questions after doing the brief of the chapter. Okay, so what is an equilibrium? So equilibrium is basically, it is when a reaction, the parameters of reaction become constant, it has attained equilibrium. It does not mean that the reaction has stopped. Yes, the reaction is going on, but it is proceeding in both directions at an equal pace, so that the parameters like the concentration of reactants, concentration of products, pressure, volume, all of these parameters in the reaction are remaining same. That is when equilibrium has been reached. Okay, so we'll move forward. So based on the extent to which the reaction proceed to reach the state of chemical equilibrium, they may be classified into three groups. The ones which proceed nearly to completion, for them K is more than 1. Then there are reaction which only small amounts of products are formed. For them K is less than 1, like much less than 1, and this is much more than 1. Then reaction in which concentration of the reactants and products are comparable. So we will define a range for all of these. So let's define a range. So if K is more than 10 to the power 3, you put it in the first category. If K is less than 10 to the power 3, you put it in the second category. Minus 3. If K is more than 10 to the power minus 3 but less than 10 to the power 3, you put it in the third category, which is the moderate. Okay, ionic equilibrium we'll cover in next class, but let's start with physical equilibrium. So best example of physical equilibrium is phase transformation reactions. For example, solid to liquid, liquid to gas, and solid to gas. In a solid liquid equilibrium, what is happening? Example is ice and water kept in a perfectly insulated thermos flask at atmospheric pressure, and at equilibrium we observe something. We observe that mass of the ice and water do not change with time. Even the temperature remains constant. These two things we have seen. Mass, total mass of ice and water does not change, temperature is fixed. What are these? These are parameters of reaction, and we can see that these have become constant. So your equilibrium has been reached. But you should not assume that the reaction has stopped, because intense activity can be noticed at the boundary between ice and water. Molecules of liquid water collide against ice, adhere to it, and some molecules of ice escape into liquid phase. Right? Their rates of transfer are equal. So system is defined in dynamic equilibrium here, and we can infer something. Both opposing forces occur simultaneously. Both processes occur at the same rate, so that amount of ice and water remains constant. So we have briefly covered the first, physical equilibrium. Next, we have liquid to vapor equilibrium. So the example that we'll take is, just we'll put a dish of water, okay, and we will observe it in a manometer. Manometer will show what pressure is there inside the container, right? So as you can see in the second container in which water is kept openly, the manometer reading is a bit higher than the first one in which anhydrous calcium chloride is kept, which has absorbed all the water present. Right? Here it is very less, here it is a bit more. So what is happening? The thing is, if you keep a dish of water in a container, water will start evaporating. And at equilibrium, the equilibrium will be set up between liquid and gaseous water. So the rate of condensation of vapor into liquid will become equal to the rate of evaporation of liquid into vapor. Okay. We can observe the we discussed in previous class about vapor pressure, how it depends on the surface, how it depends on the liquid, and how it varies in the different solutions. So if we take different liquids, okay, for example, acetone, ethyl alcohol, and water, it is observed that liquid eventually disappears in an open room. Okay, because in an open room, the vapor pressure of the liquid, it is not defined, because you have infinite amount of space for the vapor to cover. So the liquid will keep on evaporating till it disappears from the small petri dish or glass plate. Okay. You can only see the liquid water vapor equilibrium if you put it in a closed container. In practical terms, the last one is solid to vapor equilibrium. Example, we'll take camphor. We'll take camphor solid to camphor vapor. Okay. Other examples are iodine and ammonium chloride also, right? Then let's see one more kind of physical equilibrium, in which equilibrium is seen when solids or gases are dissolved in liquids. Okay. You remember when we dissolve a solid, keep dissolving a solid in a solvent, there comes a time when no more solute can be dissolved, or no more solid can be dissolved. What is that period called? That period is called your saturation. The solution is saturated and no more solid can be dissolved. In a saturated solution, what is exactly happening? Actually, there has been an equilibrium which has been set up in this. Okay. A dynamic equilibrium has been set up and it resembles this equation. The solute in the solution phase and the solute in the crystallized or solid phase are in equilibrium with each other. So rate of dissolution of sugar is equal to rate of crystallization of sugar. Both of them become equal to each other. So this was the first example between solids and liquids in a solution. This is like, they have given a explanation why it is dynamic. You can use radioactive sugar and you can see that in no time it just starts appearing in the solution also. So that means that dissolution and crystallization are occurring simultaneously. Okay. Next, we have gases and liquids. Best example, as I told you earlier also, is a soda bottle or cold drink. When you open it, some CO2 dissolved in it fizzes out rapidly. Why? Because the solubility of CO2 is different at different pressures. So at a defined pressure, this equilibrium is set up in the solution. CO2 gas and CO2 in solution. And this is governed by Henry's law, which states that mass of a gas dissolved in a mass of a solvent at any temperature is proportional to the partial pressure of the gas above the solvent. That was Henry's law we discussed yesterday. Okay. So what happens is, gas is dissolved under high pressure in a soda bottle and it is packed and given to you. But when you open it, the pressure decreases rapidly to atmospheric pressure. So a new equilibrium condition has been set up. To reach that equilibrium condition, some of the gas comes out of the solution, and that is what you hear as a fizz. Okay. Right. So for physical equilibrium, we can define a few points. In solid to liquid equilibrium, there is only one temperature, which is the melting point at which they can coexist. For liquid to vapor equilibrium, the vapor pressure is constant at a given temperature. Although the equilibrium can exist at any temperature, but the vapor pressure is defined for a particular temperature and it changes with temperature. Next, for dissolution of solids in liquid, solubility is constant at a given temperature. So we are seeing temperature relationship with some factors regarding equilibrium. And the last one, dissolution of gases in liquids. Concentration on gas in liquid is proportional to the pressure over the gas of the gas over the liquid. This is Henry's law. And Henry's law basically states that mole fraction of gas dissolved in liquid is proportional to your partial pressure of gas over liquid. Okay. There are some points regarding physical equilibrium. Okay. First is it is only possible in a closed system at a given temperature. Next, both opposing forces occur at same rate. So there is a dynamic condition. All measurable properties remain constant. Equilibrium is attained and it is characterized by constant value of one of its parameter at a given temperature. The magnitude of these quantities at any stage indicates the extent to which the physical process has proceeded before reaching equilibrium. Yeah, so this can be concentration. These characteristics can be concentration, pressure, mass, volume, anything. Okay, so we have done physical equilibrium. We'll move on to the next thing, which is your chemical equilibrium. Okay, so in chemical equilibrium, we establish equilibrium in a chemical reaction. In physical equilibrium, like we had established equilibrium between physical states, here we'll establish equilibrium between chemical reactions, right? Just a second. So let's start chemical equilibrium. If we define a reversible reaction like this, A plus B gives C plus D. With passage of time, there is accumulation of products C and D and depletion of reactants A and B, and the forward reaction is happening. Eventually, the two reactions occur at same rate. C plus D is increasing, product is increasing, and the reactant is decreasing. And at a particular point, okay, listen to this point. At this point, your concentration have become constant. See, they are flat, so they are constant. So this point will be known as equilibrium point, as you can see. Okay, this is how equilibrium is attained. Yes, equilibrium is dynamic, chemical equilibrium. Next, they have given one more example, formation of ammonia, in which dihydrogen and dinitrogen is getting depleted because their reactants and ammonia is increasing, and they all become constant at this point. So this point is known as equilibrium point, right? Okay. They have given few more examples. They have given examples of formation of HI. Okay. What is happening in this thing is they have shown that equilibrium can be attained from either direction. How? So this is the point when they reach equilibrium. Consider that you take HI as 0 in the left side and the hydrogen and iodine as the reactants. So you can observe that hydrogen and iodine reach their equilibrium concentration and HI also reaches its equilibrium concentration eventually. But if you take HI in excess in the right side and you remove the reactants, you will see that HI will start forming the reactants until both of them reaches their equilibrium condition. So you can attain equilibrium from any side. This is what they are told. Next, the formulas which are important. Firstly, formula of the equilibrium constant. Okay, Kc is the equilibrium constant and this is the formula of Kc. So Kc is basically, if you define Kc, C denotes concentration. Okay, and If you define concentration as a parameter of equilibrium, so the equilibrium constant will be concentration of products. So you have to multiply the concentration of products divided by the multiplication of concentration of reactants. This is your basic formula. And yes, don't forget to raise them to the power of the stoichiometric coefficients. We will see examples. For example, let us see this equation. Here, your statement, this is your Kc ka equation. Next, let's move on to one more equation which is known as Kp, which is defined at a constant pressure. Just like Kc is defined at for concentration, for pressure, if you take pressure or partial pressure as the defining parameter of equilibrium, you will write equilibrium constant as Kp, and it will be pressure of products raised to the coefficient, partial pressure of reactants raised to the coefficients. Okay, right. They have given a general expression for equilibrium constant of any reaction, and equilibrium constant for the reverse reaction is inverse of the equilibrium constant for the forward direction. This you can know. Kc, Kp we have done. Let's move on to homogeneous equilibrium. In a homogeneous system, all reactants and products are in the same phase. For example, they'll be in gaseous phase, they can be in liquid and aqueous phase, they can be just in aqueous phase. Solid equilibrium is very less seen because the dynamic property of the system is not there. The particles are not free to move in solid, so the dynamic nature of equilibrium cannot be set up in a solid equilibrium. Right? Let's move on. Equilibrium constant in gaseous system. So this is what I was talking about, the Kp. Using your ideal gas equation, can you convert the equation of Kc into Kp? They have defined Kp. See, they have defined Kp for the same reaction, HI wala reaction. Can you define a relationship between the Kc and Kp using universal gas equation? Yes, we can define it. We can define it as this. Okay. Kp is equal to Kc RT to the power minus 2. This is your relationship between Kc and Kp. So Kp is Kc RT to the power, this minus 2, what is this minus 2? This minus 2 is delta Ng. Okay. Okay, this is the delta N. What is delta N? Delta N is the moles of gaseous moles of product minus gaseous moles of reactant. This is the value of delta N. These formulas are quite important in your question solving. Moving on to heterogeneous equilibrium. In heterogeneous equilibrium, there are some different phases involved. For example, the first example is your phase change reaction. Yeah. The second example they've given us, this one, calcium hydroxide dissociating into calcium and hydroxide ions. Okay. Usually what you do is, in the equation of Kc, you remove the solid phase reactants. So you remove whatever reactant is present in the solid phase. Why do you do that? You do that because the volume change of the solid phase reactant over equilibrium is 0. Okay. That is why you need to remove the solid phase reactants. Only gaseous and liquid phase you'll include in the equilibrium. All right. Let's move on. Similarly, if you need to define a Kp, just use the pressure which is only going to be exerted by fluids. Okay. Now, moving on, they've given a lot of examples. Applications of equilibrium constant. Okay, we'll just give it a read. Expression of equilibrium constant is applicable only when the concentration of reactants and products have attained constant value. Then the value of equilibrium constant is independent of initial concentration. Okay. Then equilibrium constant is temperature dependent, having one unique value for a particular reaction represented by balanced equation at a given temperature. So if you change the temperature, your equilibrium constant changes. That means the condition to attain equilibrium has changed. Okay, the reaction needs to readjust itself at a different temperature in order to reach equilibrium at that temperature, because the parameters are different at different temperatures. That is the basic principle. Next point is equilibrium constant for reverse reaction is equal to the inverse of equilibrium constant for the forward reaction. Last, the equilibrium constant K for a reaction is related to the equilibrium constant of the corresponding reaction whose equation is obtained by multiplying or dividing the equation for the original reaction by small integer. Which means if you multiply an equation by 2, then you have to raise K to the power 2, right? This is what you have to do. Application is predicting the extent of reaction, predicting the direction of reaction, calculating the equilibrium concentration. These are the application of equilibrium constant. Now, predicting the extent of reaction, as I told you, if the equilibrium constant is more than 10 to the power 3, products predominate. If it is less than 10 to the power 3, then reactants predominate. And if it is between them, then both reactants and products are equally present. Okay, right. Predicting the direction of reaction. So the direction of any reaction, if you know that, yeah, so and so is the equilibrium concentration or equilibrium state. Suppose you know that, yeah, this is the equilibrium state of a reaction. If you are somewhere here or here or here, where will you try to go? You will try to attain the equilibrium state. That is what is Le Chatelier's principle. If a reaction is attaining equilibrium when reactants are more and products are less. So if you prepare a random reaction with lots of products but less reactants, what will happen? It will move in backward direction, right? So as to create more reactants, more reactants, more reactants, until products have reached their equilibrium concentration and reactants have reached their equilibrium constant. Similarly, if there is an equation in which reactants is less, products are more at equilibrium, you have known it through the concentration, through the constant, equilibrium constant. And in your reaction mixture, there are lots of reactants, so less products. Which direction will the reaction go? It will go to the forward direction to make more products and reach equilibrium faster. This is about concentration. Similarly, it relates to the pressure also. If partial pressures are known at equilibrium, which is more, which is less, we can calculate the direction. Then we come at temperature. Suppose a reaction is endothermic, delta H is positive, which means it tends to absorb heat to go in the forward direction. So if a reaction is endothermic and you increase the temperature, what will happen? It will go to the forward direction, because in the forward direction it is endothermic. In reverse direction, what it is exothermic. So if an endothermic reaction is there and you're decreasing temperature, so it will go to the reverse direction, because now it cannot absorb the heat, it has to give out the heat to make equilibrium. So if the reaction is endothermic and you're increasing temperature, yes, well and good, it will move to forward direction. If a reaction is exothermic and you're decreasing temperature, well and good, it will move to the forward direction. But if an endothermic reaction, you are decreasing temperature, it will go backward. Similarly, for an exothermic reaction on increasing temperature, it will move backward. This is all determined by the Lee-Chatterless principle. Next, calculating the equilibrium constant. Yeah, balance equation you have to write. Then you have to write initial concentration, change in the concentration, equilibrium constant. You have to assume all that as x. Then you have to write the equilibrium constant expression, calculate the equilibrium constant expressions, check your result. All of this you have to do. Now let's see the relationship between reaction quotient, Gibbs energy, and equilibrium constant. So reaction quotient is basically equilibrium constant at any given point in reaction when equilibrium is not attained. Q, the expression for Q is also same. Products raised to the coefficient and reactants raised to the coefficient. But it is not at equilibrium. Right. So delta G is negative, then it is spontaneous. If delta G naught is positive, it is non-spontaneous reaction. Why? Because the equation is at equilibrium, the equation is this. Because delta G is 0 at equilibrium, and we get these two equations which we should remember. Factors affecting equilibria. Only use Lee-Chatterless principle to determine everything. I have already covered concentration. I've already covered pressure. I've already covered temperature. Okay, inert gas addition. What is happening in inert gas addition? In inert gas addition, inert gas will not participate in reaction, right? So what you are doing, you are adding inert gas at constant pressure first. So you added some inert gas. To maintain constant pressure, the volume must increase to accommodate the extra gas. Now, if volume has increased, so the concentration of reactant and product has decreased. Now, if concentration has decreased, which means it will move to a direction where your where your more amount of matter is being formed. Let me give you an example. If A plus B is in equilibrium with 2C plus 4D, what is the number of moles of reactant? 2, which is forming 6 moles of product. If this reaction mixture, you are adding inert gas at constant pressure, so concentration of all the substances are decreasing. That means reaction will move to the forward direction to create more moles of product so that concentration might increase. And it is reverse for the reverse reaction. But if you're adding inert gas at constant volume, there will be no change in volume, there will be no change in concentration. So no change at all. Does not matter. Effect of temperature, we have covered. Effect of a catalyst. What does a catalyst do? We all know a catalyst speeds up a reaction. No change in equilibrium constant. Only temperature can change equilibrium constant. So yeah, we are officially done with the theory part. We'll move on to the questions. Yeah. So let us start with the first question. The first question says they have given a reaction A to B at a given temperature. They have given delta G naught and 22 millimoles of A amount of B in equilibrium mixture they have asked. They have given R, they have given ln10 ka value. So let us start. The equation which we know is delta G naught is equal to minus RT ln K equilibrium, right? Delta G naught is 9.478 into 10 to the power 3 joules minus 8.314 into temperature is 495 into ln K. So we have to find out ln K, right? So we will divide these two by each other. Before that, we'll multiply 8.314 and 495. So this is 4115, okay? And 9478 divided by 4115, it is basically 2.303. This comes as 2.303 is equal to ln K, and they have given 2.303 is equal to ln 10. So K equilibrium is equal to 10. And if K equilibrium is equal to 10, then product at equilibrium divided by reactant at equilibrium is equal to 10. Let us assume that initially 22 and 0, this was the concentration. Finally, let us assume that 22 minus X and X has been made. So according to the equation, X upon 22 minus X is equal to 10. So 11X is equal to 22. So X is equal to 2. That means amount of B in equilibrium mixture is 2 moles or millimoles. Moving on to the next question, the standard enthalpies of formation they have given and the standard enthalpy they have asked. Okay, this is basically a thermodynamics question. So we can skip this. Considering the reaction, N2O4 gives 2NO2. Temperature at which Kc is this and Kp is this is. So they are asking Kp is equal to Kc into RT to the power delta N. And delta N, as you can see, is 1. So this is 1. So they are asking us the temperature at which this much Kp and this much Kc is there. You also multiplied by R. So Kp they have given 600.1. Kc they have given 20.4. And R is 0.0831. Okay. So this is 30. So yeah, 375 Kelvin. This is the answer. Moving on to the next question, we have this equation. The reaction enthalpy they have not given us. They have given us bond enthalpy. Again, a thermodynamics question. We can skip this. Question number 5. Question number 5 says, this is the equation. This is the delta G naught. They have to find Kc for this reaction. So as we know, the equation is delta G naught is equal to minus RT ln K. Let's assume Kc. Okay. Good. 25.2 into 10 to the power 3 joules per mole is equal to minus R is 25/3, which is 8.3. Temperature is 400 and ln K C. So 25 you just add 3. So it comes to be 7.5 is equal to ln K C, and 7.5 2.303 into log Kc, and if you divide 7.5 by 2.3, you will have almost, wait, we have done something wrong. We'll do the equation again. This is the reaction. So 25.2 to 10 to the power 3 is equal to minus 8.3, 400, we'll come back to that later. Let's solve this question for now. So this question says that this is the reaction, and relation between dissociation constant and degree of dissociation and equilibrium pressure is given by, they have asked. So let us write the reaction again. So if initial concentration is C, so final concentration will be C minus C alpha, and initial was 0, C alpha and C alpha by 2. So K will be C alpha into C alpha to the power 1 by 2 divided by C minus C alpha. So we can write Kc is equal to, so you can cancel C with C. So C to the power 1 by 2 into alpha to the power 3 by 2 divided by 1 minus alpha. Okay, this is Kc. But we have to find out the relation between this and equilibrium pressure also. So let us keep this aside the Kc ka equation, and we'll try to find out the Kp ka equation. So for pressure, the total, let's find out the partial pressures. Partial pressure of A will be C minus C alpha upon total. What is the total moles? Total moles is C minus C alpha plus C alpha plus C alpha by 2. So C plus C alpha by 2 or 2C plus C alpha by 2. So the total pressure is, this is the partial pressure of into PT, and then C alpha 2C plus C alpha by 2, C alpha by 2, 2C plus C alpha by 2. This is your partial pressures. Writing the equation of Kp, we will write C alpha 2C plus C alpha by 2 into C alpha by 2 to the power 1 by 2 upon 2C plus C alpha by 2 to the power 1 by 2 into pressure to the power 3 by 2, which is combined for both of these. We will divide it by C alpha, C minus C alpha upon 2C plus C alpha by 2 into pressure. So you delete this into P1 by 2, and yeah, this is going to be, you have to remove all the C's. So alpha 2 plus alpha by 2 into alpha by 2 upon 2 plus alpha by 2 to the power 1 by 2 divided by 1 minus alpha upon 2 plus alpha by 2. So 2 plus alpha by 2, you cancel from here. You can put alpha, you remove these two also. So you have alpha to the power 3 by 2 upon 1 minus alpha into 2 plus alpha to the power 1 by 2, which is your P to the power 1 by 2. I forgot it. B option is correct. Next, PCl5 dissociates as this. 5 moles are placed in 200-liter vessel. 2 moles of nitrogen is there. 600 K is the temperature. Equilibrium pressure has been given. You have to find equilibrium constant for dissociation of PCl5. So 5 moles has been placed. PCl3, Cl2. 5 moles PCl5 has been placed, which already contains 2 moles of nitrogen, which is insignificant. We'll just write 5 upon 200 as the concentration. Okay. And let's assume, just a second. So let's assume we just solve by moles. 5 moles are there. At equilibrium, this is the condition. Suppose they have given us that equilibrium pressure is 2.46 atm. Equilibrium volume is 200 liters. Moles we have to find out. R we have 600 Kelvin we know. Sorry, this is 2.46 is equal to N into 1 by 12, which is the value of R. So N is equal to 2.46 into 12, which is the number of moles if we multiply 2.46 into 12, which is almost equal to 30. So we know that 200, okay, 30. It should be, we have to add nitrogen moles also. So X is equal to, comes 20. This is, I don't think this is possible. Anyways, we'll just write the value. So next question, standard free energy change for 50% dissociation at 1 atm pressure is this. The value of X is. So X is equal to minus RT ln K. Dissociation has been 50%. If this is an equilibrium, then the Kc will be defined as x squared divided by x by 2. Kc will be defined as this. Kp will be defined as oh, really sorry. So yeah, Kp is 4/3 of total pressure. And the total pressure is 1 atmosphere. So Kp is 4/3 atmospheres. So we'll put the values. R will be 1/12 for atmospheres. Temperature is 300. Ln 4/3. So X is equal to minus 25 into 2.303 into log 1.33. Log 1.33 has been given as 0.1239. And if we multiply all of it, we can find out 25 into 2.303 into 0.1239, 1.42. Next question. Two NOCl gives NO and Cl2. 2 moles of NOCl was placed in 1 liter of flask. Concentration of NO after equilibrium was established. It was found to be 0.4. Equilibrium constant they have asked. So NOCl gives 2NO and chlorine. So 2 initially there. And at equilibrium, suppose this is the state. And we know that X is equal to 0.4. So this will be 1.6, 0.4 and 0.2. So equilibrium constant will be 0.2 into 0.4 ka square divided by 1.6 ka square. And this we can 4, so 0.2 for 16. 1 by 80. So 1 by 8 into 10 to the power minus 1. 125 into 10 to the power minus 4. Moving on, 4 moles of argon and 5 moles of PCl5 are introduced into an evacuated flask of 100 liters capacity at 610 Kelvin. At equilibrium, the total pressure is this. They are asking for Kp. So PCl5, PCl3, Cl2, initially 5, and yeah, 4 moles of argon are also there. At equilibrium, the pressure was 6 atm. We can assume that this was the dissociation. Total number of moles are 5 plus X plus 4 at equilibrium. Let us find out if 6 atm and 100 liter is the capacity, then total number of moles are how much? So total number of moles are 2. This is 12. Total number of moles are 12. So 9 plus X is equal to 12. X comes out to be 3. Put 3 here. So 2, 3, 3. Total number of moles are 2, 3, 3. So 2 upon 2 by 8 is the mole fraction for PCl5. 3 by, so out of 6 atm, how much is the equilibrium mixture? It will be like 8 moles out of 12 moles, right? So 8 by 12 into 6. So 4 atm. So total pressure is 4 atm. Therefore, 3 by 8 into 3 by 8 into PT upon 2 by 8. 8 to 8 you cut down. 3 3 is 9. 8 to 16 into 4. So 9 by 4 is 2.25. That is the answer. Next, a box contains 0.9 gram of liquid water. Temperature has been given and pressure has been given as 32 torr. Volume of the box is increased. Some liquid evaporates to maintain equilibrium pressure. If all the liquid water evaporates, then the volume of box must be. So equilibrium pressure of water is 32 torr. It's 32 upon 76 mm atm. Sorry. So 0.5 atm they have given. 32 upon 76 atm they have given as the equilibrium pressure of water. So if no water is remaining, right? So 0.9 gram, how many moles are there? 0.9 gram. If we divide by moles, then it is almost 1 by 20 moles. This is the gas phase. So 1 by 20 moles are in the gas phase. Temperature is 300. R we can take as 1 by 12. Volume we don't know. Pressure we know 32 by 76. So volume we can calculate as 5 into 19 by 32. Approximately 2.96 liters. Sorry, this will be 29 liters because into 10 is also there. So 29.6 liters. Yeah. Okay. We have 3 more questions. We'll solve this. This is the Ka1, Ka2, Ka3 for the respective ionization constant of A, B, and C relationship they've asked. So if we add all these reactions together, firstly, this is the reaction. There has been a little bit mistake. So yeah, if we add 1 plus 2, we will get 3. We know this. So K1 into K2 is equal to Ka3. Then they have given equilibrium constant for this reaction. Now they are asking equilibrium constant if we half it. So 2 into 10 to the power 15 to the power 1 by 2. So minus 15, let's assume. So 20 into 10 to the power minus 16 by 2, that will be under root 20 into 10 to the power minus 8. So yeah, x is equal to under root 20. Next, 600 Kelvin, 2 moles. 1 mole of oxygen has been mixed with 2 moles of NO at 600 Kelvin. Reaction comes to an equilibrium. Total pressure is 1 atm. Analysis shows that 0.6 of oxygen is present at equilibrium. So yeah, we just have to write the equation. At initial, this is the condition. Final, let us assume 2 minus x, 1 minus x by 2. X is the thing. And we know 1 minus x by 2 is equal to 0.6. So x is equal to 0.8, 1.2 and 0.8. So equilibrium constant 0.8 square divided by 1.2 square into 0.6. So this is the thing, 9 by 16 into 6. 15 by 16 is the answer. So yeah, we are done with all the questions. So let's call it a day and all the best for your exams.